Hello and welcome to the third in a series of video lectures introducing a second course in string theory. In this lecture we'll discuss the third chapter of the notes on duality. This chapter is split into three sections. First, we introduce branes in M theory. From one perspective, the low energy perspective, these are solitonic extended solutions of 11D supergravity, or SUGRA for short. The action of supergravity in the bosonic sector has an Einstein-Hilbert term and some gauge field content. Where F is a 4 form and C is a 3 form. Hence, the counting for this final term works correctly. Determining the classical solutions is done via an ansatz, which shows that we end up with objects with 3 and 6 extended dimensions. We call these M2 and M5 branes. These are conjectured to be the stable objects of M theory, a higher energy generalization of 11D supergravity. Indeed, we can argue that they're stable because they couple to the 3 form and dual 6 form gauge fields. So any charges will be conserved in interactions. In the second section, we discuss branes in superstring theory. It turns out that the alpha prime tends to 0 limit of superstring theory gives you 10D supergravity theories, of which there are 3 flavours matching the flavours of superstring theory, type 1, type 2a and type 2b. In fact, 11D supergravity most naturally reduces to type 2a supergravity via the so-called dimensional reduction scheme. This immediately allows one to identify the stable branes in superstring theory, or at least some of them. From the M2 and M5 branes, we obtain 4 different types of branes, namely the NS1, D2, D4 and NS5 branes, depending on whether the M branes wrap the compact dimension in the dimensional reduction scheme. The nomenclature depends on whether these branes naturally couple to the NS sector, or in the case of the D branes, the Ramond sector. Why is that? Well, it turns out that by a famous argument of Polchinski, the Ramond sector coupling is equivalent to coupling to open strings with Dirichlet boundary conditions. This argument is clearly explained in the accompanying notes. Viewing the branes as independent objects in their own right in superstring theory leads to a different interpretation, namely that branes support gauge theories. In particular, a stack of n branes gives you a UN gauge theory. This can be derived by observing that the D branes are exactly generated by the excitations of open strings carrying the appropriate Chan pattern color factors. Finally, in this section, we discuss the ADS-CFT duality, perhaps the most powerful method in contemporary theoretical physics. There are 2 fundamental claims. Firstly, that bulk string states VI, which we can think of as vertex operators, correspond to boundary operators OI in the CFT. Secondly, that a correlator in a string theory on ADS of such vertex operators is exactly equal to a correlator of the associated CFT operators. We can verify this in various limits by looking at a supersymmetric Wilson loop due to Maldacena. And indeed, there have been many subsequent checks of more non-trivial examples. A key component in such checks is the so-called GKPW formula, which provides a helpful way of relating general correlators in the limit where we have a strongly coupled CFT, which turns out to correspond to a supergravity theory on the ADS side. The formula says that the partition function in the CFT with source g of x is the path integral in the supergravity theory where we specify a boundary condition on that path integral, that the fields have to end on g of x. At this point, I suggest that you look at the notes for much more detail and explicit calculations relating to all of the above points. Thank you for listening.